When we look at fire management in the natural environment, one of the central questions is what effect does fire have on the flora, fauna, and soils of that environment? We generally divide these effects up into either first order or second order effects. First order effects are the burns and injuries caused directly by a fire, whereas second order effects refer to the changes in habitat that affect the recovery of the species. As well as providing modelling of fire behaviour from plant traits, FRAME is also the first tool of its kind to enable modelling of first order fire impacts on flora, fauna and soils. In this module, we'll go over the main functions that FRAME provides to model these impacts. The core of all fire impact modelling in FRAME is the threat function. Threat calculates the radiative and convective heat fluxes to a point that you nominate in the forest structure or the vegetation structure. So, given its distance from the flame and its height in the structure of the vegetation, threat finds what the convective temperature is and the air movement is, also whether the convective plume intersects the point, and finds the radiative heat that's transferred to that point. In contrast to some other approaches, threat utilizes a moving flame to calculate changes in radiation and convection over the course of time. So if we are looking at a convective plume, for example, as in this diagram, the plume will only intersect a point if the flame is pointing in that direction. So as the flame approaches, the plume may not be intercepting the point, whereas there may be radiative heating of the point. At a certain time, the plume will intersect the point, providing a big pulse of convective heat, and then once that passes, there'll be some convective and radiative cooling. The FRAME functions that utilize threat offer the option of continuing the calculations after the flame front has passed. This is important for a couple of reasons. In the wake of the flame front, you tend to have coarser fuels that continue to burn and continue to provide heat. These are most important to features close to the ground because the flames are smaller. In addition to this, though, heat can take a while to conduct through surfaces. So, for example, if we're looking at an animal sheltering inside a wooden hollow or under the soil, the surface of the tree or the soil has been heated by the flame, but that now needs to conduct into the soil. Conduction is a much slower process than heat transfer by radiation or convection, so we need time for that heat to conduct down into the soil or into the wood and potentially reach the animal and affect the animal there. There are 7 functions in FRAME for modelling first order impacts. 4 of these are for flora and soil communities, and 3 are for fauna. The first of these is the soil function, which models the heat profile in the soil over time. This allows us to look at fire heating effects on soil communities of bacteria and fungi, as well as seed storage and effects of heat on physiological factors such as germination. I'll demonstrate the use of the soil function using this example from an area of alpine ash, Eucalyptus delicatensis forest. This area had not been burnt for about 33 years. As you can see, there are scattered shrubs and the occasional taller mid-story plant like the Exocarpus species. A prescribed burn was planned for this area with the intention of reducing the fuel loads to reduce the bushfire risk. These include the surface litter, which is visible in this photo, along with that shrub layer. A common rule of thumb is that low intensity fire, such as prescribed burning, won't germinate leguminous plants which have a physical dormancy. Physical dormancy means that heat will break a protection on the seeds, allowing them to germinate. I'll run the frame model using the soil function to estimate what the soil heating will be here. So that happens in two stages. Firstly, to model fire behaviour for the site, and secondly, to model heat penetration into the soil. This study is detailed in the Frame 2021 paper in Methods in Ecology and Evolution. We'll use the same input files here for alpine ash that we've used in previous work and run this using the probfire function. Now in this study I've set jitters to 10, which means there are 10 replicates or 10 random points picked across the forest floor. In the frame paper you'll notice there are 50 replicates, which gives a slightly different curve, capturing a little bit more diversity and a bit of a smoother response. After running probfire, we then load the database, run frame summary, and here I'll add on a new field to give the calculated biome intensity. Then we'll also run the rep flame function to capture the diversity in flames second by second. The next line there calculates the litter depth, working off the rule of thumb that 5 tonnes per hectare is 1 centimetre of depth. Finally, we then run the soil function there, inputting each of these parameters. The value there called step refers to the depth that we're going down in the soil. You can see this on line 14. We're going down 0.01 of a metre or 1 centimetre, where we calculate each temperature. The surface value there is 450, which is an estimate that the temperature directly beneath the burning litter is 450 degrees. We then add in the relative humidity, which affects the radiation impacting the soil, moisture content of the soil. The values distance and trail refer to the distance away from a point on the ground that we're modelling fire from. So we're looking at there the distance in metres from which radiant heat will start to heat the soil, and trail is the number of seconds after the fire has passed. So you can see that we're counting on quite a long flame residence time there. var is the variability in flame angle, and then we've got a few different other parameters that affect the radiation from the flame, the radiant heat impacting the soil, the texture of the soil, clay loam, and the peat content, the grain, the fact that it's not a frozen soil. These factors all affect the rate at which heat conducts down into the soil. I've graphed the modelled output in two different ways here. Graph A on the left shows the time trace of temperature at each of the 1 centimetre depths into the soil, and graph B on the right shows the maximum temperature reached at each depth in the soil. There are a few features to notice in graph A. Firstly, the lines are fairly jagged there. Now, as you can see in the graph from the methods paper, this is less so when we run more replicates, because we get more of a smoothed average function for fire behaviour. But here we can see more stark definitions in the nature of the flame front that passes through an area. The next point to notice is this flattening of some of the lines at the 100-degree mark. This happens due to the evaporation of water from the soil. The latent heat of evaporation prevents the temperature from rising for a little while. Now, for the soils closest to the surface, that effect is negligible or impossible to even notice at the 1 centimetre depth. But as you get deeper into the soil and the rate of heating is slower, this delays the temperature for some time. You'll also notice that when a more surface soil delays in its heating, then the layers beneath it slow down in their heating as well. On the right hand arrow, you'll notice that as the surface soil continues to cool after the front has passed, it eventually reaches a point where the surface is cooler than the deeper soil. And once that surface soil is cooler than the layers beneath it, then the layers beneath start to cool faster. Most of the heat that's coming into that surface soil is now rising back up out of those deeper layers. On the right hand graph, you can see that the black line showing the maximum temperature reached at each layer stays to the right of the two vertical red lines. Now these lines mark 60 degrees and 100 degrees. These are the general rules as to where the soil seed bank will be affected and the ways that it will be affected. Temperatures above 100 degrees, which is the full depth that we've modelled here, are too high for seeds, and seeds in those depths down to 5 centimetres will probably be killed. Temperatures below 100 degrees but above 60 degrees are generally the right range of temperature to break the physical dormancy of those seeds. In this example then, we can see that down to 5 centimetres the heating into the soil was probably so great that it killed the soil seed bank to that depth. Now if we go deeper into the soil, however, the temperatures would be suitable for germinating seeds. If you compare that to the modelling in the frame paper, which used a larger number of replicates, we can see the heating is not so extreme, and there was actually likely germination in the upper few centimetres of the soil. So how did this prediction compare to what actually happened at the site? In this photo we can see the original area on the right hand side of the track and the area that was prescribed burnt on the left hand side. A closer look at that area on the left hand side shows us a dense cover of germinated Divisia latifolia. We can see then that the ability to model soil heating with frame now facilitates better planning around the effects of fires in the soil environment. The first order effects of fire on plants can be captured using the two functions, Flora and Girdle. Flora calculates both the amount of foliage that is consumed directly by fire and the amount that is scorched. And so Flora can be used to calculate fire severity to compare with satellite measured values. Girdle calculates heat penetration into the stem of a plant. It takes its name from the phenomenon of tree girdling, which is when heat penetration kills the cambium of a tree. This has a delayed effect on the life of the tree. The tree will die as a result of it, but it won't necessarily show up as dead in satellite imagery straight after a fire. Because of this, fire severity mapping can at times underestimate the severity of a fire in areas where trees are susceptible to girdling. For this example, we will look again at the same alpine ash site. Alpine ash trees are susceptible to being killed by 50% crown scorch. Also, saplings of alpine ash trees can be killed through girdling. So to calculate this, we've entered these values in the first 4 lines. Sapling bark thickness and tree bark thickness are 1 centimetre and 4 centimetre values, and the thickness of the phloem for each of those trees is also given there in metres. To calculate plant scorch and consumption, we use the Flora function here, and we've set the value test to 80. Test defines the temperature at which we say foliage will be killed by scorch. So if the leaf is heated to about 60 degrees, generally the cells die, and the approximation here is that if that will occur if the surrounding air is about 80 degrees. When we run that function, we also mutate two new columns to determine whether 50% of the mid-story or the tree canopy have been scorched. If that happens, we count it as those strata being killed. To calculate girdling effects on trees, we need to specify a height that we're measuring that temperature penetration at, and we've set it here at 0.1 of a metre. Heat penetration is also affected by the density of the wood of the tree, the density of the bark, as well as the factors we mentioned before, the thickness of the bark and of the phloem. Rough bark can also catch fire, and when it does so, we've added in a value here of res bark, which is the flame residence in the bark, and just set it to a standard value of 45 seconds. Com bark is the temperature beneath the burning bark, and this is taken from a small number of studies that have given it approximate values. We've also added in values for wood moisture, just called moisture, and bark moisture, which is B moisture, as well as the standard values describing atmospheric conditions for radiation transfer. The distance value is the distance from the tree where the fire is at the point where we start to model, and trail is the number of seconds that we'll continue to model afterwards. There are two new values introduced here. One is the temperature of cell necrosis, which is set to the standard value of 60 degrees. That's the value nect. And the other describes the rate at which flame height in surface litter declines. That's surface DECL. The girdle function will run quite slowly because it's calculating heat fluxes at 1 second intervals as the flame approaches and after the flame passes. In contrast, the Flora function calculates a single value based off the average flame descriptors for the area. When we summarize the modelling from this, we can pull out a few values such as flame height, 1.4 metres, flame length is 1.5 metres, rate of spread in kilometres per hour, Byram's fire intensity. They're all sort of more standard fire behaviour parameters. But when we start looking at the effects on the plants, we can look at the percentage of shrubs that were scorched and the percentage that were consumed. So 100% were scorched, but only 20% of the shrub layer was actually consumed by fire. 33% of the mid-story was scorched and 20% was consumed. And 3% of the canopy was scorched, and there was no canopy consumption, there was no crown fire. Now the mid-story was killed by scorch for 10% of the area, but that's only considering scorch. We can also see that girdling was likely here. Now girdling here I've set to either a true or a false value based on the calculation. So trees were girdled if heat was able to penetrate in as far as the cambium in that calculation. I've repeated those calculations for the canopy, and none of the canopy was killed by scorch or by girdling. So we could expect this prescribed fire to kill the mid-story of alpine ash saplings, but not kill the tree canopy. These effects were visible in the survey I conducted through the area, which showed none of the older original mid-story saplings, but a lot of young regeneration, and no stags left of killed mature trees. It seems that the prescribed burn left those untouched. When we look at heat penetration into the stems, we can see that in the top example, looking at saplings, first of all, if we can look at the legend there, the depths have divided the distance down to the cambium in equal values. So the distances calculated there are much smaller than in the mature tree, where we're looking at a total distance of 5 centimetres. So again, in the sapling example at the top, we see much greater heat penetration into those shorter distances, as we would expect. You can start seeing, as you get deeper into the tree, that effect of water as temperatures hit the 100-degree mark, and there's a delay in heating. You can also see the red line, which marks the cambium, does reach that boiling point of 100 degrees. It doesn't pass it, but that's over the 60-degree mark, and therefore the cambium's killed in those saplings. That's made a little more explicit in graph B at the top right, where the vertical red dotted line marks the lethal temperature of 60 degrees, and the horizontal red line marks the point where we're entering the cambium area. So the black line is the maximum temperature reached at that depth, and we can see that it is to the right of the vertical line the whole way down. So including in the cambium area, it is over the lethal temperature. In the mature tree, the effect is quite different, because we're dealing with thicker bark to start with, and so we've got a lot further for that heat to penetrate. Again, we can see that the second centimetre into the tree, the temperature doesn't exceed 100 degrees because of the water effect, and that blocks the deeper areas of bark and phloem from heating. And as a result, if we look at graph D, we can see that the black line there passes to the left of the lethal temperature. So once we're getting below the horizontal red line, temperatures are still just within the safe range. So we're not expecting any girdling of those trees from that model run. Frame offers 3 functions for calculating fire impacts on fauna: underground, hollow, and mammal. The underground function uses the same sorts of inputs as previous functions we've looked at. So we'll look here at an example using both hollow and mammal. The example looks at a case study of the Ngwea, or western ringtail possum. It's a critically endangered possum living, in this case, in a patch of tuat woodland in southwestern Australia. Ngwea will often nest in hollows, such as in this example, but in other cases they will build a dray or a nest in the fork of a tree or somewhere exposed. A hollow like this is largely protected, but because it's open at the end and also has cracks along the side and holes in other parts of it, it's also partially exposed. To calculate risk to this population, then we'll use the mammal function to look at animals that are in exposed drays, and the hollow function to look at animals that are in sheltered tree hollows. Both of these functions calculate a degree of protection to the animal depending on their location. So the hollow function has to first of all transfer heat through the wood protection, whereas the mammal function transfers heat through the animal fur or pelage. And this is why it's called the mammal function at the moment, yet we've only got values for mammal fur. Some other studies have also used these mammal fur properties as approximations of insulation by feathers, for example. You can see that the mammal function also uses measurements of body length and surface area of the body mass, to describe the shape and size of the animal, and this affects the amount of convective heat transferred in. We've also got a series of values protection, fibre count, fibre diameter, fibre CP, skin CP, skin density, and skin K, which all provide descriptions of the thickness of the animal fur and the density of the fur, the fineness of the fur. They also describe the specific heat and thermal conductivity of both the fur and the skin of the animal. The shape parameter refers to the shape of the animal, the body shape of the animal. It comes from a very simple set of formulae for convective heat transfer models, and generally we can describe an animal as having a cylindrical shape, so call it a cylinder, but the other options are also flat or sphere. The mammal function calculates heat transfer into the animal across several layers. These include the fur, but it also divides the skin up into 3 layers based on the body mass. These layers are the epidermis, the papillary dermis, and the reticular dermis. It's generally accepted that when a large heat source causes second-degree burns or burning of the papillary dermis, that burns will also occur in the respiratory system, and these will almost certainly kill the animal. Calculating these impacts requires, again, the same sorts of outputs as before. So we run the fire model for the Tuart woodland, and in particular we will make use of the ignition paths output. As we can see here, there is a bulgur grass tree located directly beneath the dray for the possum, a dray located in the hollow, and both convective and radiative heat is calculated for each second and each flame segment that's shown in this diagram, for example, as well as for flames from the surrounding plants. When we look at the heat fluxes from that, we get 3 results as shown here. The top graph A, shows the heating for exposed animals in this instance. We can see that the surrounding air gets to temperatures over 500 degrees, and that causes heating of the reticular dermis, which is the innermost layer of skin, full thickness burning, shown by the red line in this instance, that approaches burning temperature. The papillary dermis, which is the dark line, goes well above the burning temperature. So we've got second degree burns, partial thickness burns, which will kill the possums that are exposed at this particular height where we're looking. Graph B shows heat penetration through the wood of a hollow, and the red line shows the temperature within the hollow there. And again, the temperature here has passed above a critical level. Now, on the surface of things, if you compare the temperature within the hollow, which is the red line on graph B, to the temperature that the exposed mammals are exposed to, you can see that they're exposed to a much lower air temperature. The difference with a hollow is that they're within a trapped environment, and what tends to happen here is that the humidity is also trapped within the hollow. So if we use what is known about that effect, we actually see that respiratory injuries occur at much, much lower temperatures when this occurs. And so again, it's very likely that the animals within the hollow here also didn't survive. Graph C is a graph of the amount of radiation reaching the hollow there. Now, I've included this out of interest to look at the question of what form of heat transfer actually causes the higher temperatures in the hollow or at the exposed animal. And so if we look at where the temperatures rise in, say, graph A and B, we can see that there is a big pulse of convective heat right at the point where radiant heat drops down lowest. And this is also where the body temperatures and the hollow temperature rise fastest for the animals. So heating of the animals is occurring by the convective heat flux that happens as the flame passes beneath the hollow. The radiant heat flux is actually lowest at that point, because to get a large radiant heat flux you need a large face of a flame, which tends to happen when the flame is either side of the hollow. So you can see that radiant heat flux decreasing as the flame moves away. In this module then, we've covered advanced techniques for modelling first order fire impacts on flora, fauna and soils. This can be achieved using the function soil to look at the soil environment, flora to look at consumption and scorch of plant foliage, girdle to look at heat penetration into stems and the potential for killing plants in that way, underground for looking at fire effects on animals sheltering underground, and the functions hollow and mammal for looking at animals that are either sheltering in hollows or mammals that are sitting in exposed situations.